Alright, so this is just a quick video on how to use Octave Online for part of the experiment for Chapter 5. So we're looking to see how fast our sequence is converging to zero. And so that's actually an interesting question. We'll talk about that in class, but we're given that each of the functions below has a fixed point and the orbit of 0.2 is attracted to this point. So for each function, use the computer to compute the orbit of 0.2 until it reaches the fixed point, or else comes within some designated distance, say 10 to the minus 5. Okay, we say that it reaches that fixed point if we're in there. Yeah. In actuality, we never actually hit the fixed point. But getting back to the question, what am I trying to do here? I want to list each of these functions, find the fixed point, find the derivative at the fixed point, state if the p is attracting or neutral. That's just whether the derivative is equal to 1 or in absolute value or less than 1, right? Then the number of so this is where you use the computer, it's just this last piece. The number of iterations necessary for the orbit to reach p. And so we want to spit out the iteration on which the distance from the orbit of 0.2 and 10 to the minus 5, or between 0.2 and the fixed point, is less than 10 to the minus 5 power. Okay, so I'm giving you the first 4, and so we will, in this video, we'll do E and F. Okay, so let's see what happens with those two functions. First off, I need the fixed point, so you can use the computer if you need to. We can solve 0.4 x times 1 minus x equals 0. I guess it's, equals x, doesn't it? So you have to put in the right equation. X equals minus 3 halves and 0. And so nicely, Wolfram Alpha gives you the plot too, so you can do a little cobweb diagram. So it looks like if you do a little graphical analysis here, the orbit of 0.2 will be converging to 0. Okay, so now I go over to my, oh, by the way, what's the value of the derivative there? So the derivative of my function is 0.4 minus 0.8 times x, right? And so at 0, it should be 0.4. I would be writing this down, right? But so the summary here is that for this part, the fixed point is 0. The value of the derivative is 0.4, and so p should be attracting. And so the number of iterations necessary is the last piece. So now I'm going to go over to my Octave Online. I'm going to put in a new function. Let's see, which one is that? That one. Good. Okay. And so now I go to my script. Good. Okay, and now let's see. My initial point is 0.2, so I'm just going to say, maybe I'll just say x is equal to 0.2. And then I'm going to define the function, and we're going to define this as an anonymous function, which means I'm going to use the at and then parentheses x, and now I put in the definition of the function. So in this case it's 0.4 times x times 1 minus x. Okay, so now my function is defined. So for you, right, this would stay the same, and you would just change this piece. Good. And now we want to put in a loop. Oh, maybe I should put my fixed point in here too. Let's say c is equal to 0 in this case. Okay, so you would change that to your fixed point whenever you get that. And now we can say for k equals 1 to, how many iterations should we run? How about, we want a lot of iterations here. 500,000. We'll break out of the loop if we finish early. And then we'll just say, let x new be equal to f of x, right? And so now I want to check to see if my point is in the orbit, or is within 10 to the negative 5 of x0, which is c, which is 0. Okay, so is, well, I need an if statement then. So if the absolute value of the difference, x new minus c, is less than 10 to the minus 5 power, I better put the parentheses around the -5. Then what I want to happen is I want it to break out of this cycle. So I'm going to print fprintf. This is why you can just use this code here. Fprintf number of iterations is %d, and then that's going to be the value of k. Okay, and then we just break out of this loop and end. Okay, and then finally I need to end my loop. Okay, and so now I'll save this file, and now I'll run the file. Oops. Let's cancel that. I made an infinite loop, didn't I? Do you see what I forgot to do? I forgot to set x equal to x new again. Okay. Now I shouldn't have an infinite cycle. Run. There we go. So it took 11 iterations in this situation to move to the fixed point. Okay, so now that I've got this all set up, right, for part F, I just have to change my fixed points. My fixed points here are 0 and 1, right? And I know that the derivative then is going to be 1 minus 2x. And so at 0, the derivative is 1. And so that's going to be neutral. And so the orbit should be, the orbit may converge to 0. Let's see if it does. So I'm going to change my definition now on line 5. In fact, one good thing is to keep the old function and just put a comment symbol on the front so that you still have it. And then f equals at x. And then my function is now x times 1 minus x. Be sure and put the multiplication sign in there. And now the rest of this is exactly the same. Okay, so I save, and now I'll run it. Well, I guess I can go ahead and just hit run. See what happened? It took 99,985 iterations to get to within 10 to the minus 5th power of our of the fixed point. Good. And so this is the big difference now. So now you would record those numbers on your homework sheet, right? So those were the number of iterations necessary for the orbit to reach 0.0 in this case. Okay, so those are the solutions to E and F. And so go ahead and maybe I'll just save this script file for you. I'm not sure that you can read it well on this video, so good. That's it for now. See you in class.